Here we go. All right, so today's topic is gas stoichiometry. And as I mentioned, because we can calculate number of moles from the ideal gas law, we can obviously do some stoichiometry, right? That's the premise behind gas stoichiometry. The ideal gas law gives us moles, so that means we can do any sort of stoichiometric calculation we want. So let's do this one together. Waters form from the reaction between oxygen gas and hydrogen gas. If you begin with the following, and these are your temperatures, volumes, and pressures, how much water can you form? So I want to know the mass of the water. What mass of water? So the hydrogen gas is at 25 degrees Celsius, 2.8 liters, 1 atmosphere. Oxygen gas is at 28 degrees Celsius, 3 liters, 1 atmosphere pressure. So what we're going to do, we need to write a balanced equation, right? You can't do any stoichiometry without a balanced equation. Now, we're going to figure out number of moles of each reactant. How would I get that? If I've got temperature, volume, and pressure, that's everything I need for PV equals nRT, right? Because R is just a constant. So I can use PV equals nRT to get number of moles for hydrogen. I can use PV equals nRT to get number of moles of oxygen. Now, because I know number of moles for both of these, is this going to be limiting reagent? Yes, right? I have to figure out which one I run out of first. So I get number of moles of this, number of moles of this. I'm going to do the stoichiometry twice, right? And then it's just, you know, like we've done 100 times already this semester. Does everyone understand the action plan? This is basically just regular stoichiometry 2.0, right? The only difference is you're going to have to use the ideal gas law here to get number of moles. When we first learned stoichiometry, we started with a mass in grams, right, which we then converted to moles. Then we did the mole ratio. Well, we don't have mass in grams, but we do have temperature, volume, and pressure. And since these are gases, that gives us number of moles. Does this make sense? Okay, so first we need a balanced equation, right? You can't do any stoichiometry without a balanced equation. 2H2 plus O2 produces 2H2O. All right, now we're going to use the ideal gas law. If PV is equal to nRT, how do I get N by itself? N is just PV over RT. Right? If I want N by itself, divide both sides by RT. So PV over RT gives me number of moles. And so let's calculate number of moles of H2. Plugging in my data from the problem is all I'm doing. Right? I'm just plugging in my data that I was given. So the number of moles, I mean the pressure is 1, volume's 2.8. This is a constant, and then I convert Celsius to Kelvin, right? PV over RT. Now we got to do it for O2 as well, right? So 1 atmosphere, 3 liters, R is a constant, and then 28 degrees Celsius would be 301 Kelvin. So back at the beginning of the semester when we first learned stoichiometry, we started with a mass in grams and we converted it to moles, right? Well, we don't have that ability now, but we get number of moles from the ideal gas law. Is everyone with me on how I did this? Just plugging into PV equals nRT, solving for N. Because I know number of moles of both of these though, this is limiting reagent, right? I have to figure out which one of these I'm going to run out of first. So obviously I'll have to do the calculations for 0.114 moles of H2, how much water can I form? And then 0.121 moles of O2, how much water can I form? And then which number do I pick, the smaller number or the larger number? The smaller number, right? So everyone with me on the game plan here for what we're doing? Makes sense? Got like a rip in my straw. So my straw is not very useful anymore. Let's get a new one. Okay, so now it's just stoichiometry like what we've done in the past. Right? For H2, mole ratio is 2 to 2. Molar mass of water is 18.01 grams per mole. You could have done this as one calculation and then calculated grams separately as a separate calculation. Or you can do it all at once. Okay. There's my 0.121 moles of O2. Mole ratio is 2 to 1. Again, molar mass is 18. If you wanted to do this calculation and then do this calculation separately, that's fine. If you wanted to do this calculation and then this one separately, that's fine. You'll get the same result either way. Picking the smaller number, right, would be the 2.05. Now, in terms of my sig figs, I believe my pressure only had 1 sig fig in it. So technically my final answer shouldn't be 2.05. What should it be? It should just be 1 sig fig. Right? Carrying out extra digits, but then we round at the very end. My pressure only had 1 sig fig. So my final answer is only going to have 1 sig fig as well. Make sense? Does everyone see how we did this? So I've got several problems for you to do. I'll put a problem up, pause the recording, you give it a try, we go over it, and then I think we'll be able to get to van der Waals equation today too. If we can't, that's okay, we can talk about it next time. You try this one. Hydrochloric acid, HCl, formed from hydrogen gas and chlorine gas. If you begin with the following conditions, what mass of hydrochloric acid could you form? Hydrogen gas at 30 degrees Celsius, 1.4 liters of it at 1.2 atmospheres pressure. Chlorine gas is 26 degrees Celsius, you've got 1.9 liters of it, under 1.4 atmospheres pressure. All right, let's look at this one. So we have to first write a balanced equation, right? Hydrogen and chlorine gases are both diatomic. So we calculate number of moles for each one of these. 0.0675 and 0.108 is what I got. Did you get something similar for number of moles? Now we're going to do the limiting reagent calculation. Mole ratio is 2 to 1 for both of them. So then all I have to do then is convert to grams. Rounding our final answer to 2 sig figs, 4.9 grams is the final answer. Do we agree? Are you getting to the point where doing PV equals nRT makes you kind of want to scream? Because if you are, that's good, right? Because that means that you've mastered it. Try this one. The Haber process occurs when hydrogen gas and nitrogen gas produce gaseous ammonia. If you begin with 2.5 liters of hydrogen gas at 27 degrees Celsius and 3.0 liters of nitrogen gas at 29 degrees Celsius, and they're both at 1 atmosphere pressure, what pressure will be exerted by the ammonia at 78 degrees Celsius if its volume is 5 liters? So think about what this problem is asking you to do. Come up with a strategy and solve it. I'll pause the recording. All right, let's go over this one. So this one's slightly different. All right, we still have to figure out number of moles of each of my reactant. It's still a limiting reagent problem. But now we're figuring out what information about the product. Are we figuring out its mass? Would that be useful information for us? No, it wouldn't be beneficial to us to figure out the mass of the product because the problem asks what pressure will it exert if it has a temperature of 78 degrees Celsius and a volume of 5 liters. All right, so if I can calculate number of moles in, R is a constant, there's T, there's V, I can solve for P, right? So I'm going to do PV equals nRT 3 times. I'm going to do it twice at the beginning for my reactants, and then I'm going to do it again at the end with my product. So first thing I want to do is calculate number of moles of each reactant. So there's number of moles of H2, right? N is equal to PV over RT, all right? If PV equals nRT, how do you get N by itself? Divide both sides by RT. So number of moles of H2, I got 0.1016. And for N2, I got 0.1211. Do we agree? Left off a parenthesis there on both of those. That's kind of funny. Questions on how we got number of moles for each reactant? All right, now we're going to do stoichiometry, but we're only calculating number of moles, right? We don't need to know mass in grams, because if we convert it to grams, we're going to have to undo that and convert it back to moles, because we're plugging into PV equals nRT. Right? N is what we're interested in finding here. So now it's limiting reagents. Right? For the H2, the mole ratio is 2 to 3. And for the N2, the mole ratio is 2 to 1. So that means that the limiting reagent here is the hydrogen gas. Right? So that means that the moles of NH3 is 0.06773. I'm carrying out extra digits because I'm going to round at the very end. Do we agree on the stoichiometry part? Now, you could have carried yours differently in terms of decimal places. We're rounding at the end. Is your answer within rounding of mine? 0.068, 2 sig figs. Now that we know number of moles, the problem gave us the volume and the temperature of the NH3. So we're just going to plug in and get pressure, right? Number of moles is what I just solved for. R is a constant, and the temperature convert to Kelvin, right? So liters cancel, let's see, moles cancel, Kelvin cancel, I'm left with atmospheres. Rounding my final answer to 2 sig figs, I got 2.0 atmospheres. Do we agree? Get something very similar? What'd you get?
0.4.
0.4. Okay, what was your number of moles?
That's what I have.
Do you have the same number of moles? Okay, so maybe I typed something in my calculator wrong. 0.06773 times 0.08206 times 351. I forgot to divide by 5 because 1.95 is what you get, but I forgot to divide by 5. Good eye, good eye. So 0.39. Good catch. Yep, forgot to divide by 5. See, teachers make mistakes too. All right, here's another one for you to try. This one's a little bit different, right? All of these gas stoichiometries are going to be slightly different. That's the fun part. That's the beauty of it, right? You can have lots of variety. A sample of solid calcium carbonate decomposes to form 4.7 grams of solid calcium oxide and 5.1 liters of gaseous carbon dioxide at 42 degrees Celsius under 4 atmospheres pressure. What was the mass of the original solid calcium carbonate? How much did you begin with? Pause the recording. All right, let's take a look at this one. So we're wanting the mass of the original sample. We know information about the 2 products of the decomposition reaction, right? So we're going to work backwards to figure out what the original mass of the sample was. So we know the mass of the product, and then we know the volume and temperature and pressure of this gas, right? So we can do stoichiometry from here to here, stoichiometry from here to here, and then compare. So getting number of moles of each product. For the calcium oxide, we're just converting grams to moles, right? Because we know its mass in grams. So that's just converting to moles using molar mass. To get the number of moles of CO2, N is equal to PV over RT, ideal gas law. Right, so P and V divided by RT, 0.789. This is limiting reagent because we know number of moles for both of these. So we're going to do some stoichiometry. So mole ratio is 1:1 for both of them. And then the molar mass, I just rounded to 100. Save space on my slide. Again, if you wanted to do this as one calculation and then do this separately, that's fine. If you wanted to do this as a calculation and then do this separately, that's fine. But when you compare, you take the smaller value, right? Rounding our final answer to 2 significant figures. 8.4 grams is your final answer. Do we agree? Right. So anytime you know information about 2 substances, it's a limiting reagent type problem. We're starting to see a pattern here on how we use gas laws in stoichiometry. Try this one. Here's a little picture representing it too. A sample of solid potassium chlorate is heated in a test tube, and it decomposes into solid potassium chloride and oxygen gas. 650 milliliters of oxygen gas were collected over water. Okay, so here they are, bubbling up, at 22 degrees Celsius and a total pressure of 754 torr. The vapor pressure of the water is 21 torr. What was the original mass of the potassium chlorate sample? So I'll pause the recording, give you a few minutes to attempt this one. This one's a lot easier to deal with because why? Is this one limiting reagent? No, it's not. right? I didn't give you the mass of the solid this time. I just gave you information about the gas. So that means I don't have to do 2 calculations. I have to do 1, right? But the one thing I do have to deal with is I have to factor out the fact that this was collected over water, right? Because this is being collected over water, there's some water vapor in here as well as the oxygen gas that I'm interested in. Right? So I have to subtract out the vapor pressure of that water. And then I have to convert torr to atmospheres before I can plug it in. So getting number of moles is the same as it has been for the past several problems, PV over RT, right? So pressure and volume, because this was a 650 milliliters, so I need to convert to liters. There is R, and then there's my temperature in Kelvin. Don't forget to convert torr to atmosphere, right? Divide by 760. And so that gives me number of moles of O2. And now stoichiometry, I don't have to do limiting reagent. Mole ratio is 2 to 3, and the molar mass is 123 approximately. Rounding my final answer to 2 sig figs, I got 2.1 grams. Did you? Did you get something similar? Yes? All right, try this one. I think this is the last stoichiometry one we're going to do. Then we'll do van der Waals. 35 liter sample of oxygen gas under 1.25 atmospheres at 31 degrees Celsius is mixed with 2.8 liter sample of methane, CH4, at 25 degrees Celsius under 1.65 atmospheres. The mixture is ignited, carbon dioxide, water vapor form. What kind of reaction would that be? Combustion, right. Calculate the volume of carbon dioxide formed if the pressure is 2.5 atmospheres and its temperature is 125 degrees Celsius. All right. So this is a limiting reagent problem. Right? We have to calculate number of moles of each reactant using the ideal gas law. And then we use stoichiometry to get number of moles. Now I've condensed a lot of stuff here on this slide, right? This is the number of moles, mole ratio is 1 to 1. This is number of moles, mole ratio is 1 to 2. So picking a smaller number of moles. CO2, I got 0.189. And now using the ideal gas law to get volume, just like in the previous problem, we used ideal gas law to get pressure at the end. Now we're using ideal gas law to get volume. Do we agree? We agree? Okay, let's talk about the van der Waals equation. This is the last new information before your next exam. So we call it the ideal gas law because we make some assumptions. When we do PV equals nRT, we're making some pretty significant assumptions. We're assuming that all gases are acting in an ideal way, right? If the way we want them to behave. Now, reality, there's no such thing as an ideal gas. No gas is going to truly follow the ideal gas law to the letter. Because, now I know that's a lot of writing, right? We're telling ourselves that there are no intermolecular forces. In reality, there are going to be a small degree of intermolecular forces, right? We also tell ourselves that when gas particles collide, there's no transfer of energy. In other words, it's elastic collision. But in reality, if 2 gas particles collide, they do slow down a little bit. So they are not truly elastic collisions. And then the biggest thing, the place where you see the effect of this greatest, is at really high temperature, really low temperature, and then extreme pressures as well. So this is the van der Waals equation, which takes this into consideration. So if you're looking at your data, okay? So this is PV over RT, right? What would that be? What value is PV over RT? What variable would that be? N, right? So that's number of moles versus pressure, okay? So if you've got 1 mole and then pressure, if it's an ideal gas, right? We're just going to have this nice straight line. But notice if you're at a really low number of moles here, so we've decreased number of moles. But the bigger issue is, look at the temperature variation here. So again, we made some assumptions in the ideal gas law. The ideal gas law is a really simplified formula, okay? But it really breaks down when you get to high pressures and really low temperatures. That's the thing you need to jot in your notes, okay? You need to use the van der Waals equation instead of PV equals nRT if you're at really high pressure or really low temperature. Those are the two places where the ideal gas law kind of falls apart. And I'm going to show you two scenarios, one calculated using the ideal gas law, one calculated using the van der Waals equation. Okay, so if we're at an extreme temperature, extreme pressure, PV equals nRT just kind of falls apart. And so we're using the van der Waals equation, which will be given to you on the exam on the reference page. I'm not going to make you memorize this. Okay, now this handout that I gave you, here's the van der Waals constants. So each gas is going to have its own A and B value. Okay, so these A and B values are corrections to factor in the intermolecular forces and all that great stuff that I just mentioned. Okay, so A and B are unique to each gas. So for instance, if we're doing it for xenon, right, A is 4.19, that goes in right here, and B is 0.0511, goes in right there. N is still number of moles, P is still pressure in atmospheres, V is still volume in liters, R is still the gas constant, okay, T is still Kelvin temperature. But I'm not going to show you the derivation of the van der Waals equation, because that one is kind of nasty. I wouldn't make you derive that. If you take physical chemistry, which, you know, I hope I've talked you into becoming a chem major, you'll spend a lot of time talking about the van der Waals equation and where it came from and how it works. You'll spend a long time talking about that. So this is the version I gave you, van der Waals constants. So I would obviously have to give you this. I'm not going to make you memorize van der Waals constants. That's just insane. So let's look at this two different ways. What is the pressure when 5 moles of krypton is in a 4.7 liter tank at 890 Kelvin? Would we consider that an extreme temperature? Yes, that's a really high temperature. So we're going to calculate it two ways. We're going to calculate it using the ideal gas law, and then we're going to compare that to what we get when we use the van der Waals equation. Okay? And again, A and B are constants for each gas. So I would give you this, and I will also give you the van der Waals equations. All you have to do is do the arithmetic. So here's what we get with the ideal gas law. P is nRT over V, so that gives me a pressure of 78 atmospheres. That's what ideal gas law gives me. Van der Waals equation, so P plus N squared, A is the constant, right, for krypton, 2.32, divided by V, that's the volume squared, so that quantity, times, and we're just plugging in, 4.7 minus 5 times B, times number of moles, right, for krypton. B is 0.0, right, krypton, 0.0398, equals 5 times R times T, right? So we're solving for P here. So we do a whole bunch of reduction. So we get 84 atmospheres versus 78. Is that a significant difference? It's a really significant difference, right? So if you're at an extremely high extreme of high pressure, really low temperature, right? You've got to use the van der Waals equation, because the ideal gas law, those little assumptions that we deal with at 1 atmosphere pressure, they really fall apart if you're at a really high pressure. Right, so 78 versus 84. So you try this one. You've got just enough time. What's the pressure when 5 moles krypton in a 4.7 liter tank at 650 Kelvin? Calculate it with the ideal gas law, and then calculate it with the van der Waals equation. And while you're writing, I'll just talk so that it's recorded in the video. Okay, what conceptually do you need to know about the van der Waals equation? Obviously, I'm not going to make you derive it. I'm not going to make you, explain where it came from. But what do you need to know? You need to know when to use it. Okay, so what physical conditions need to use the van der Waals equation, and why we have it. Why do we have the van der Waals equation? Well, we have the van der Waals equation because the ideal gas law makes some assumptions. The ideal gas law assumes that there are no intermolecular forces. The ideal gas law assumes that all the collisions are elastic, right? That there's no transfer of energy. In reality, there are some problems with that, right? There are some small intermolecular forces, and there are not perfectly elastic collisions. So the ideal gas law especially shows those glaring deficiencies when you're at extremes. All right, now I'll pause the recording, give you a few minutes to work on this. Okay, I know you may not have completely finished, but I know most of you are pretty close, and we're running short on time here. So here's what I got with the ideal gas law. That one shouldn't have taken you more than a couple seconds to do. Did you get 57 atmospheres for PV equals nRT? Now when you use the van der Waals equation, it might have taken you an extra minute or two. But I got 68. Did you? That's a pretty significant difference, right? 57 versus 68. Oops. Yeah, 57. I wrote 51 there. Versus 68, right? You get a very different number with the van der Waals equation. And again, the van der Waals equation takes into consideration the identity of the gas, right? And it takes into consideration the intermolecular forces, the non-elastic collisions, all that great stuff, right? Which make their appearance really, really noticeable at those extreme situations. All right, so this is where the information for exam 3 ends. So anything we talk about after this will be on the final, but it will not be on exam 3. So I hope you have a good day. See you tomorrow for lab.